Welcome everyone. Today we'll be presenting about our project. So the name of the project is Real Estate Listing System, which implement the data structure of binary search tree. A real estate listing system is a platform that allows users to search, filter, and manage property listing efficiently. By utilizing a binary search tree, which is BST, as the underlying data structure, the system ensures fast and efficient operation for adding, searching, and display property data. Next.
And next, I will present about how application works. So there's three operations. The first one is add property. Users can add a new property listing by providing price, location, and ID. Next is search property. Users can perform a search for a property by entering search criteria such as a specific price or property ID. And lastly, the display property. List of available properties sorted by price or property ID. Next. The data organization and storage pattern in the system is first one, data organization. The core data property listing in the real estate listing system is stored in the BST, where each node represents a property listing. There is three identifiers. The first is price, location, and property ID. For the storage pattern, the binary search tree nodes are typically stored in dynamically in memory. Each node contains data and also left and right pointers. Okay, next. Okay, for the first operation, add property. This operation allows the users to add a new property to the listing. The property is inserted into the binary search tree based on its key value. For example, here is price. The system ensures that the property is placed in the correct position to maintain the binary search tree properties. For example, here the illustration. First, we have the root node, and then after that, you will add a new node with the value of 8 and compare to the value of the root node. So the value of the node 8 is smaller than the root node 60. So it will go to the left. And after that, a new value node is added, which is the value of 74. The value of 74 is much higher than the root node of the 60. So it will go to the right. Okay, next. Okay, for the next operation is search property. The system traverses the binary search tree by comparing the value with the current node's data and move left or right accordingly until the desired property is found. Okay, for example, let's say that the target value is 45. So you can consider this as the pricing or the property ID. So first, we will go through from the root to compare the target value and the value of the root node. So we can see that the 45 is much smaller than the value of the root node, which is 60. So it will go to the left. And then it will compare the value of the target value with the node of 8. So the value of 45, it will go to the right because the value of the 45 is much higher than the value node of the 8. Okay, next. And lastly, the display properties operation. This operation use an in-order traversal method, the in-order print tree method and it helper function in-order print tree in-order print tree. This is the method in the algorithm. It guarantees that the properties are displayed in the sorted order, for example, as ascending price or property ID. So the sequence of the traversal of in-order method or in-order traversal method is from the left to the root and go to the right. Okay, this is example of an illustration. First, it will go from the 60, and then from the root. I'm sorry. It will go to the far left of the search tree, the binary search tree, which is the value of 5, and then it will go to the root, which is 8, and then it will go to the right, which is 45, and goes back to the root node, which is 60, and lastly, from the root to the right, which is 60, all the way to the value of 95. So this is the example of the display properties. So we can see that the value is go from the follows from the lowest, which is the value of 5, to the highest in order. So in a sequence. So we can see that this is a selling price. Okay, that's all. I will just pass to the next presenter.
So for running time analysis, I pick search. So for the big O complexity is O log of n. However, from our case, we have 3 cases. Our best case is O of 1. This is constant. So this is only if what we want to find is at the root. So it only take only one search. And the average case is O log of n for BST. So this is for a balanced tree where every parent has 2 child, left and right. The worst case is O of n. This is for an unbalanced tree where every parent has only 1 child. So let's say you have 1 parent and then everything is the child value, everything is lesser. So it goes like everything to the left. Or maybe if the root is just not a number and then the child is a value bigger, then it will just go straight to the right. So it is unbalanced. So the time complexity is linear O of n. So okay, next slide. So steps to derive efficiency. Let's say suppose we want to search for a property with price 200 in the following tree. So we start at the root node, which is 250. So since 200 is less than 250, we move to the left. And now we are at 150 node. So since 200 is more than 150, then we get the key. We get the key matches and the search terminates. So the search only took 3 comparisons proportional to the height of the tree. So O log of n for balanced tree. Okay, next slide. This is a sample application for a search function. This is Java. So it takes in price and node. And so if node is null, return null. So if price is higher, so return price and node right, else return left. Okay, so next slide. So our conclusion on the efficiency, the search operation in a BST is efficient for balanced trees, offering a complexity of O log of n. However, for unbalanced tree, the complexity becomes O of n, linear. So to maintain efficiency, self-balancing BST such as AVL are recommended for systems that require frequent searches and dynamic updates. This reduces the risk of performance degradation. That's all from me. I will pass to the next presenter.
So for the next part, identify the collection class. So the collection class used in this code is BST class. It functions as a custom implementation of a collection-like structure, which is a binary search tree. It holds nodes of property objects and provides methods to insert elements, which is insert, traverse and print all elements in sorted order, which is in order print tree. Search for elements based on a key, which is fine. Okay, so for the next slide, for the identify the interface, we only have 2 interface, which is the implicit use of the comparable interface, and for the second one, interface for the input and the output. Okay, so next slide. So for the list operation in the collection class, so for the operation in the property class, we have property. This is string ID, string address, double price, in size, which is a constructor. We also have get price and toString. So for the operation in the node class, we have node, property, which is a constructor. So next slide. So for the operation in the BST class, we have BST insert, private insert, in order print tree, private in order print tree, find, private find, is BST satisfied, private is BST satisfied. For the next implicit interface operations, which is compared to and toString. So that's all for me.
So finally, in the conclusion, there's a 5. So first one is efficient property addition, which means when the user adds a property, the BST dynamically insert it into the correct position based on the key, such as price or ID, ensuring the tree remains sorted. This efficient organization is key to quick retrieval. Next, the dynamic updates. What it means is the system handle updates in real time, so adding the properties doesn't disrupt the structure. Then the optimized search. Operation like searching remain fast due to logarithmic time complexity of balance BST. However, I point out this performance depends on keeping the tree balance. So if the tree unbalanced, we will go to the summary number 4, which is the limitations. In an unbalanced BST, operation can degrade to linear time, similar to a linked list. A self-balancing tree like an AVL tree will address the issue, which could be enhancement for future iterations of the system. Last but not least, the practicality. This system is practical choice for organizing real estate listings because it inherently supports sorting and searching, which are critical for property management platform. So this is our reference, and that's all from us.